Nonconformists could take a page from the proton's playbook. The subatomic particle is once again resisting scientists' attempts to size it up. Everyone agrees the proton is tiny, its radius is less than a femtometer, or a trillionth of a millimeter. But scientists still don't agree on exactly how small it is. A new measurement supports the case for a smaller proton, physicist Lothar Masenbacher and colleagues report in the October 6 Science. But in some sense, it deepens the puzzle, says Masenbacher, of the Max Planck Institute of Quantum Optics in Garching, Germany. The researchers peg the proton's radius at 0.83 femtometers, whereas the textbook value is 0.88 femtometers. That might not seem like a huge difference, but the few percent discrepancy is stymieing scientists' attempts to test quantum electrodynamics, the theory of how electrically charged particles behave. In the past, scientists gauged the proton's girth in two ways, by firing electrons at protons and measuring how the electrons ricocheted, or by zapping hydrogen atoms with lasers, to study the atom's energy levels, which depend on the proton's size. Those measurements were all in agreement. But in 2010, a team of scientists figured out a way to make proton radius measurements much more precise. The researchers studied energy levels of muonic hydrogen atoms in which the electron is swapped out for a heavier relative called a muon. Such measurements found that the proton was about 4% smaller than previous estimates, or about 0.84 femtometers. Physicists struggled to explain the discrepancy. Some suspected that the mismatch could be hinting at undiscovered physics, such as a new particle that interacts with muons but not electrons. Now, by making an improved measurement of energy levels in regular hydrogen, Masenbacher and colleagues find a small proton, in close agreement with the muonic hydrogen measurements. That suggests that a difference between electrons and muons is probably not the culprit. Still, the researchers still can't explain why other techniques get different results. Electron scattering experiments, for example, point to a larger proton. It's a great result, but unfortunately, I would say it made it even harder to see what's happening, says physicist Jen Bernauer of MIT, who is not involved with the new study. It remains unclear whether the larger or smaller size is correct, Bernauer says. The proton puzzle persists.